Fitting XPS data from start to finish. Here I will use a simple file like STO, the strontium titanium oxide. So the structure of the STO was shown in previous YouTube videos, and it is made of raw data which are added in column A and B starting at row 1, and that's the same for each core levels. Okay. So now we can drag the sample, the data into the plot, and then start the fitting. Let's use a background. We'll use the default method, which is the multi-region smart. Let's go from here to there. Okay, and then let's use an LA in this case, so that which is an LA is widely used with CASA, so people are more familiar with LA. And let's use a doublet. Let's fit this. It's done. We get a value of 2.9 to the power of the Lorentzian. So this is the Lorentzian, which has been powered by 3. And if I just go down, we can see how more or less well it fits. From here, it looks good, an RSD of 2.4. So this is an STO single crystal. So I'll call it SR lattice. I can also call it SR lat. Then the legend is updated. We can, if we want, remove this if we create a single word. So I can use something like this to create a single word, and now the legend, the pic disappeared. Okay, let's go to the next one, and let's create a background. Now we have the oxygen 1s. Let's create the background. Let's use again the LA as we started using LA. Here we'll use a single pic for the oxygen lattice, and then there will be the CO, C double bond O, C single bond O, OH pic in here. And I will use the same width for both. So I will, not the same width, sorry, the same shape. And the same shape here is fixed using the gamma. So the gamma is the shape on the right side, but because it's a symmetric pic, because it's 50%, sigma equals gamma. So that's our sigma, and that's our gamma power. Let's type A on this grid, A, and A will become A times 1. So B now, for the gamma, is in function of A. And if I let it fit, because the width will be broader there, so we cannot fix the width to the same as A. And now we get a quite good fit of RSD 2.12. You can see that is fitting quite well. Okay, so this is our oxygen lattice. And this is our oxygen surface, CO, OH. So we can call it how we like. This text is from Matplotlib, so you can really create anything that Matplotlib allow you to create. For example, if you had a pi star satellite, you just create something like this. Pi dollars, so you put it in between dollars, and that will become a pi. So everything that Matplotlib allow, this also is able to. Okay, so let's call it OH, and let's go into the next model. So this is the carbon 1s. Let's add the background. So there's not much carbon on this crystal. We've kind of created a background. Let's add some peaks. This time, so I will move them. Again, using the tab on Q, I can change which peaks I want to move. I know I have a CC peak here, I've got a CO, and I've got a C double bond O or OC double bond O here. And this time I will fix my width, fix the shape to the peak A. I may just move this one because I like to start first from low binding energy to high binding energy. So let's add the next peak. And that will also be in function of A. So I only need to type A and no need to type ×1 because this is the default. And then the shape should be the same. And again, all of the symmetry is fixed. Yeah, I could put it in function of A. If A was asymmetric, then it will then be the same for all peaks. But this time it's all fixed. Now let's fix that. Let's fit the peak, sorry, and we get something like this. Now we have 3 peaks. Let's call it adventitious. So it's at 284.55. We expect it, in my case, I expect it to be 284.8. Some people like to use 285. It's as long as it's described in your report or paper, it is fine. So now I have 3 peaks and the legend is all updated. I will then go to the titanium 2P, so that seems quite difficult. And again, this is a LA. This time I may use a void because I don't like the way the LA fit the titanium 2P. As you may know, the LA is not a true peak. It has no meaning. So now I add the doublet. I get this. And for titanium 2P, the width of the 1/2 is different to the width of the 3/2 due to the Coster-Kronig effect. Okay, but the area is half of the 3/2. So that we are allowed to have the same, half of the area, but the width will be different. So let it vary. And the shape will be the same as A because it's a doublet. Let it fit. And you can see what I was mentioning is that the LA is not able to fit properly here. So I will not use an LA in this case and simply use a void function and fit the widths. So in this case, I'm going to fix the widths. Sorry, I'm going to unfix the width of the sigma, which is the same because the width of the Lorentzian is already fixed using this LG ratio. I'm going to let it vary by just deleting. And now it goes from 0.0123. This is the standard, but the area is the same, or half of the titanium 2P 3/2, and then the shape is also constrained to the 3/2 for peak B. So let it fit, and now it fit very nicely. So I'd rather use this one. Okay, so this one is our TI lattice. Maybe I'll just zoom out because I've seen that it works well. TI lattice and TI lattice. I may choose to show this peak or not. So if I create a single word, then the label is not shown. And now we have all our data done. I may want to to just zoom onto that. So I can use something like the shift. In here, by the way, I was using the control left or right brackets to shift between each picks, but I may decide to do the shift left, and now I can move. I can just zoom onto the oxygen 1s because I've got nothing. I've got nothing in here. So, okay. I may decide to do the same for the others. So this time I'm going to use Control plus to zoom, and I zoom into so I use Control plus to zoom, and then Control left or right to just move the plot. I can do the same for titanium 2P. Maybe this time I may want to show them. I can't. There's not much data, so let's do it like that. So I may want to show this one. And that is it. It is done. And so now I can look at the quantification. So this was done on a thermo instrument. And so I can just check my preference, what I have in my instrument setting. And for thermo or avantage, I've got the letter A. And for CASA, I've got the letter C. So this is all the different instruments available. For thermo, the default RSF or sensitivity factor is AL thermo 01. So this is there. And then the method, the best method to use at the moment is the TPP2M method. There is the Schofield method, which is only a factor by K to the power 0.6. But the TPP2M is the one used by thermo. And the data that we get from KherveFitting match exactly what Avantage provides. So let's save that. I may also, looking at this, if I'm not happy with the different colors, I may just decide to use the hatch. And for example, here is a different type of hatch pattern. I can use this one, for example, different type. If I show now this one here, I can show that I can have a hatch, and I can have a not a hatch there. I can go to the next one and change this to a hatch, and maybe change the pattern to, let's say, some kind of colors. And then all of them will be like this. You can change the alpha or the the transparency of the pick. And you can see at one, you can see it well, and obviously like that. Let me go back now to solid. That's my preferred type. And let me change this alpha to something like 0.5 or 0.6. Okay. And I can also change the outside of the shape. I can decide to have a transparency, let's say, of 1, let's say, just to show what this does. So this is black, same color, so a gray and yellow. I personally prefer black with a bit of alpha, something like that. You can change the thickness. Okay, and let's save that. If I'm not happy with the font in this time I've got Calibri. And if I want to change the font, you saw where it was, but I also have possibility to change the font here. And this time they will all change to what you want. And this happened to all plots, so they're all the same thing. Let me just move it somewhere there, something like that. And now I will add it to the results table. So now I've checked the instrument, and I will maybe not add the CC because I don't really care about that. Oh, there's one thing I haven't done is maybe the peak corrections because we can see the binding energy correction. This is not done. So let us go to this one. So what this icon does is it does an automatic binding energy correction. So it's looking for the carbon 1 SCC in any of those page of those core levels. So if I just click it and we are going to go simply to carbon 1s right now, and you can see it's 284.55, so that should be 0.25 if I want to put that to 284.8, and I can be, as I said, anywhere, and you should see the value written here. And now everything has been shifted and the value is 0.25, so everything has been corrected. All those positions have been corrected to that, and as you can see it's 284.8. And now I am ready to export that to the result grid. So let's say we've added the oxygen lattice and we can see the area we had here and the RSF used by the AL thermo 01, which is shown here. And then using the TPP2M, the normalized area provided. And this is the one that give the atomic concentration if it is selected. So let's add the others. So I use the titanium 2P and then the strontium 3D. And just like Avantage, I would only select the main doublet, so the main pick. So this is obviously oxygen 1s, it's 1. And then I can choose the titanium 2P 3/2. And if I was to choose the titanium 2P 1/2, they should have the same width. Obviously, Avantage has decided that the RSF will be 2.06 and 4.42, and that actually dictate the concentration discrepancy. Okay, so let me remove that. And if I use the strontium 3D 5/2 now, okay. So now I'm getting, and I've checked it with Avantage, I'm getting the same value. I'm getting the atomic concentration that's close to a 1:1:3 ratio, and it's different. It's like this, it's the surface, and it's different, I'm not sure why. Okay, so now let's save the data. We have everything we want. So when we save the data, let me close this. When we save the data, at the moment it's not saved. We have different choice. We can save the PNG. We can save just the sheet we have. And that, by doing this, it will save the page, strontium 3D, and it will create a JSON file, JSON with all the peak fitting data that we have, not just for strontium 3D, but for everything that we've used. It will also save the background data inside the JSON, and it will save the XY data. But we also have a save all, and that will go through every core levels, just like so. And now this will actually, obviously, update the Excel page, the Excel file, but it will create a results page at the end. So let me show you what happened to the SrTiO file. Okay, so if I just start with titanium 2P, we have now the page that has been created. And then we have the binding energy like before, but the corrected binding energy is here with the residual, the background, and the envelope here with the two core levels. And then on the right side, so if I just zoom out, on the right side, this is the peak fitting table. From the peak fitting grid, so this one here, if I go now to the, so it is that one, okay? There are some hidden values, so you're seeing different columns here, which can be accessed through this button. And that provides all the different column values, so absolutely everything. But we don't need most of it, so we only need to see the most important. And this is the same now for all the other pages or core levels, together with oxygen, carbon 1s, and then a result table here. Okay, so we see, for example, the atomic concentration is shown here, and the different transmission function, which is set to 1 for K alpha, because it's already corrected inside the raw data, and the energy correction factor that we use TPP2M, and the sensitivity factor that we use the ALCM001, and the different fitting models. If you like, you have a choice of creating a report, a Word document report, and that will be in your export in here. Okay, so now if I go here, I should have, if I just refresh this, I should have a report done. Oh, it's open on another screen. Let's hope that, no, okay, that's good. Let me just zoom out. So it will create a page, very similar to the Excel, but in a Word format. Okay, so you're ready to provide the report to your manager. Okay, you can also export the file or the picture as a PNG, SVG, or PDF. Let's try PNG. And that should create something here. Let's do a PD, SVG, PDF. Okay, so it's here. And if you want, if you know about Python, you can also get a Python plot using matplotlib. It's a basic one, but it's good enough with all the pick fitting inside the raw data. Okay.